and we're going to kick off with Dr. Ellie Sansom from Curtin University talking about meteoroid orbits, and maybe we'll learn something about where Merch came from.
Hi guys, thanks for sticking around so far today, and thank you all for having me here, and so many of us from the Space Science and Technology Centre at Curtin. It's been fantastic to have such an enthusiastic audience, and I'm really excited to share some of the science that we do over at Curtin. So, who here saw Murchison? I know we've kind of had hands up before. Who here's seen a shooting star? Oh, good, at least lots of you have seen that. So basically what we do at Curtin, we're trying to take pictures of these really, really bright shooting stars, and we call them fireballs. And fireballs are the ones that are possibly able to drop meteorites on the ground. So this is a picture taken at night time. We've got all the stars in the background. I know Murchison was seen during the day, but basically we're trying to get these really, really bright shooting stars. So here's a Google Earth map of Murchison. And actually on the Met Bull, where the meteoritical bulletin where Murchison's entered, you can actually download the little map, and you can open it in Google Earth that shows where all the little, a lot of the meteorites were actually found, which is really cool. So we know it was coming in from this direction here, and a lot of you heard the sonic boom, but there weren't all that many people that saw the actual fireball. There's two recorded in academic papers, and there's quite a few more that I've been speaking to this weekend, which has been really exciting, saying that you saw it too. And we can triangulate or figure out where that fireball was coming through the atmosphere from people just observing. But we kind of need a few more than 4 or 5. This is how many saw fireball pretty much earlier this year over, this is Florida, and the eastern USA. There's about 984 observers. They all recorded their sightings, and we can actually figure out. Obviously, some people think that it was going that way. Some people will think it was going that way. But those people that logged on online and recorded their observations within 24 hours all got it pretty spot on. So we've got this fireball here, and they can figure out that maybe it dropped a meteorite around there. So they did this for the Murchison meteorite, for the 2 observers and a bunch of people who saw the smoke as well, and trying to do stuff with the sonic booms, and they figured out an orbit for Murchison, which is really cool. It was actually by someone up here at Shepperton and someone up here in Mildura, and they managed to figure out a possible trajectory for Murchison. Now, the thing is, we can kind of figure out where it came through the atmosphere, but the really, really uncertain thing is how fast it was going. And humans are actually really, really bad at timing. I had a colleague that had a little movie clip of an animated fireball going across the screen. She handed it out to a couple of thousand people and said, how long is this little animation? Most people said about 3 to 5 seconds. And then she said, actually, that was 7.5 seconds long. And she shows it again, and this time you're counting, and you're like, oh, no, that's got to be different. It can't be the same thing. But it was, and actually, so we're really bad at gauging how fast things are going. And so how the speed that came in at is really uncertain. And that's what determines how far out that rock came from in the solar system. So let me explain this plot to you a little bit more. Out here, this dark red ring is Jupiter. We have the first terrestrial planet in the middle here is Mars, and then we have Earth here, and we were about here when Murchison hit, and we thought it was going fairly slow enough to catch us up. So with that assumption, you can come up with this first orbit. If it was going a little bit faster, so rather than going 13 kilometers a second, it was going 14 kilometers a second, it goes out to this one. And we have recorded fireballs at the Desert Fireball Network that come in up to 72 kilometers a second. So if 14 is an underestimate, and it can actually, if it goes over 16 kilometers a second, it becomes what's called a hyperbolic orbit, which means it comes from out of our solar system entirely, and that is very, very unlikely. So we're still not quite sure where the Murchison meteorite came from. What a lot of people are trying to figure out is whether any known comets or asteroids are in this region of the solar system that maybe we can try and match it to. And that's still a debate that's going on today. So when asteroids are in the asteroid belt, how do we even get fireballs and stuff from the outer solar system getting delivered to Earth? When they collide, they manage to come through our atmosphere, we see the nice bright shooting star, and it can land on the ground. And we can observe the chemistry of these meteorites on the ground, as you've heard in so many talks this weekend, to try and figure out what was happening at the very, very beginnings of our solar system, when we had a really young sun. Where did life come from? Where did the water come from? All of these questions we can answer in meteorites. But of the meteorites that we've actually recovered, it's been mentioned a few times, there's about 60,000 meteorites in collections around the world. There's a really small percentage that have actually been observed to fall. And of those that have been observed to fall, so Murchison is somewhere in this Teely region here, there's only been a really small amount, this green area here, that have been photographed, and only an even smaller number that have been observed by these things called camera networks. So of those 60,000 meteorites around the world that we are using to understand how the solar system formed and why there's life on Earth, there's 37 ever that have accurate orbits. So we only know where 37 of these rocks come from. So for geologists, you can give them it's like saying, here's a bucket of rocks. Now you tell me about how the Earth formed. You can have to use that to figure out the theory of plate tectonics. You need to use that as the theory of how we get volcanoes and all of that. You can't do that with a bucket of rocks. You need to know the location of where they come from. So where in the solar system are our space rocks coming from? And the idea of the Desert Fireball Network in Australia is to figure out the orbits of these incoming space rocks so we can give that context. Where do these rocks come from? So we have about 50 cameras across Australia. We've got another 50, 60 around the rest of the world. And we are taking pictures of these really bright shooting stars that we call fireballs. Now we do that with, so these are our camera systems. We've got some solar panels. They normally have 3G connection as well, so we can talk to them remotely. And inside, it's all pretty off-the-shelf stuff. We didn't want to spend too much money on getting things specially designed. We basically got a Nikon DSLR in here. We've got a fisheye lens, like you saw at the beginning, that's taking a full image of the sky, and we've got some hard drives in there as well. And although we keep absolutely everything we see, so these guys are taking pictures from dusk all the way through till dawn, and the pictures they're taking are about 25 seconds long, so we're looking at those long exposure images. And if it sees a fireball, these guys are really clever. We've got some software in there, and they can actually figure out if there's a fireball in their images, and they send us a little email saying, hey, I think I found a fireball. Now, at the beginning, it sent us back a lot of rubbish. We got a lot of satellites, we got some airplanes, we got some pictures of birdie bums, but we've got these things called neural network, and they learn. Every time we say no, it gives us better and better results. So those send back the fireballs that we're interested in, but we keep all the data anyway. And we're actually now, all that data is coming back to Perth. We're actually starting to find some really cool stuff, like astronomic transients, like supernova. So we can see supernova with these things, which is really cool. So back in 2015, we got this image. These 4 images are from around Lake Eyre in South Australia. We actually captured it on 12 cameras. These are just the 4 closest ones. And when you look on a map, we do this thing called triangulation. So from these 4 cameras, or actually there's 5 cameras pointed out there, we can figure out where that fireball came through the atmosphere. A bit like those people we were trying to do with the human eyewitness observations for Murchison. And we saw this and we thought, oh wow, it's fallen right on a salt lake. Man, that's going to be super easy to find. Now, these two cameras up here actually don't have internet connection. They're too far away from any signal. So we had to send some guys over to go pick up the data. And while they were at it, they thought, why don't we take a scenic flight over the lake and see if we can find anything? Not that we're going to. But they saw a splash on the lake. It was really cool. I'm not going to call this a crater, because craters actually have to excavate a lot deeper than that. But we did see this splash on the lake. Now, it took us a couple of weeks to arrange everything to get out there, especially seeing as this was significant land for the local Aboriginal community. But we got out there and it had rained, so there was no longer any signs of that splash. So we got the airplane back out again. They did some search patterns, and once from the airplane you could just about see it. So they managed to go across this salt lake and dig up what we call the Meteoroid meteorite. And I really like it because it's heart-shaped. And there's a picture of them there, and these are the two Aboriginal guides that came along with us and really, really helped us out. So we've now got this guy, Meteoroid, and this is our really nice orbit that we have around in the solar system, and that's halfway just between Jupiter and Mars, so we know it's a main belt, came from a main belt asteroid. Now we now have 5 of these guys, and we have over 1,500 orbits of fireballs. Now, we don't have cameras everywhere. We can't see all the sky in the world. So we've come up with this, where people are, is normally quite light polluted, so we don't have cameras in cities, but you're in cities, and we have people in cities. So we've come up with this app called Fireballs in the Sky. So if you see a fireball, or even a shooting star or a meteor, you can tell us about it. So you can say whether you heard a sonic boom. So if you had Murchison, you'd have hit yes. And you can say, all right, I think it started somewhere over by that star, and I think it ended maybe over those trees around by where that star was. And the really cool thing about this is at the next stage, it gives you a little animation. And we're a lot better at estimating timing and speed when we have a little animation in front of us. You can say how long you thought it was. You can say, like Murchison, that it fragmented into lots of little pieces, and how bright it was. And the bit that I really like is you can say what color you thought it was as well. And it's quite fun just pretending that you saw a really bright pink fireball. So I think the next one, I'm pretty sure I'm making, pink's way more fun. I'm pretty sure I did pink at some point. Anyway, so you can report that to us and how many fragments you think it saw as well, which is kind of cool. And so you can have a go at making your own fireball or shooting star. You don't have to send it to us. We won't really acknowledge that you've sent us stuff by accident unless someone else reports the exact same thing, which is where we can start using human beings and using those hundreds of visual observations to get trajectories. Now, the other cool thing that you can do if you want to have a play with this app is it does meteor showers. It's going to do the meteor showers. Not sure if it's going to go on to the meteor showers. So if you want to know when the next meteor shower is going to happen, you can click this thing about meteor showers, and it will point you towards where you should be looking to find where those are going to be coming from. Though that does work for both the northern and southern hemisphere. So if it's pointing at the ground, it doesn't mean it's broken. It just means you can't really see it in the southern hemisphere, unfortunately. So that's our Fireballs in the Sky app, so you can have a play around with that. And I'm going to leave you with this visualization of our 1,300 orbits up until 2017. Now this is the Earth in here, and these yellow lines are all the orbits we've calculated, and all the blue dots are the meteoroids coming in. And when we get a meteor shower like the Taurids here, you can see in a few minutes we're going to get bombarded by a lot of things coming in and hitting us. So we do get hit by about a couple of 100 tons of material a day, but normally small stuff. Here's the Taurid meteor shower coming in here as well, which produces larger things. So, any questions?
Thanks, Ellie. I think, Ellie, you're our most disciplined speaker and stuck to her time limit rigidly, so others take note. But do we have some questions, please?
At the back.
Right.
Just a quick question. When the Murchison meteorite
a very good question. So for most of our fireballs, they come in, like I said, anywhere between 72 kilometers a second. We don't have very many of those. They're normally associated with the Perseid meteor shower, and they come from really, really far out in the solar system. And the slowest we have is just over 11 kilometers a second, and 11 kilometers a second is actually the limit for things that is called the escape velocity of Earth. So anything that's less than that is actually gravitationally bound around Earth, and anything less than that, we're waiting for it actually, because it means it's going to be space junk. And we're waiting to get our fireballs from space junk, which is going to be really cool. But everything we've seen so far has been just over 11 all the way up to 72. And they start burning really, really bright. So meteors are actually really small. They're probably about the size of a grain of sand. So when you see a shooting star, you're actually looking at something about that big that's burning up in the atmosphere. And actually 97% of what you see when you see a shooting star is the atmosphere burning, not the rock itself. So those are really small things. They usually come from comets. When we go, meteor showers are when the Earth flies through the tail, or where a comet has been in the past, and we get all of that dust from a comet, and we know where those comets are, so we know when we're going to hit those meteor showers, which is how we can predict them. The fireballs are actually larger material, and we think that most of it comes from the asteroid belt, where it's not predictable. We can't predict where that large stuff is coming from. So those really small shooting stars that you see start probably at about 100. I actually have a slide for this. Here we go. So shooting stars actually start at the meteors. Shooting stars usually start up here at about 100 kilometers altitude. And they burn in about this area up here. Don't normally make it to around 80. 80 is really high for shooting stars. But these really big, the big stuff we see, like Murchison, usually starts at around 90 kilometers and will burn down all the way to about 35 kilometers. Anything lower than that is really, really likely to drop a meteorite. So the lowest we've seen in the Meteoroid meteorite was 27 kilometers altitude. So although it just looked like it was just there, it was still actually really, really high. And that's actually something that we have to try and figure out, because if our fireballs stop burning here at about maybe as low as 25 kilometers up, we can't see it once it's not burning anymore. There's no light, they're dark objects. So we have to try and model where on Earth these meteorites are going to land without actually being able to see it. So we have to use wind models, and the wind is actually really, really strong at those altitudes and can really affect our fall lines. So when we have a rock like Meteoroid, it actually didn't come straight down to the ground like this. It actually got blown around like crazy, and the line where we predicted it to have fallen was actually a couple of tens of kilometers away from the line of the trajectory, which is actually quite interesting. Though we did find Meteoroid within 100 meters of where we thought it was going to be. So.
Ellie, I might just interject there. So, say with something like Murchison, when you get the sonic booms, and when the thing actually from fireball to suddenly exploding, can you calculate what height that is generally going to occur at? Does it depend on the mass? Does it depend on the composition, mass, everything?
So when the explosion, fragmentation, when things fragment, it's really unpredictable, and that is. So my role in part of this Desert Fireball Network is to model this burning trajectory to figure out if there's anything left. And the bit that really, really annoys me is when rocks fragment, because I can predict how nice it's going to slowly get smaller and smaller and smaller if it stays as one whole solid body, but it rarely does. And yes, when it breaks apart, it is very much to do with its composition and how strong that rock is itself.
So it could be highly variable.
So it could be highly variable.
Okay.
But then that sonic boom thing is actually quite interesting too, because there's two types of sound that you're getting. One's actually coming from the trajectory itself. It's coming down like this. It's the sonic boom that you hear, like if a jet's traveling faster than the speed of sound, you get the normal sonic boom. But then if it explodes, you get what we call a blast wave. And those two actually can interact and make it, rather than one big boom, you might get quite a few, one after the other. So.
In the middle of it is.
Yes, you do.
So is it always green?
No, it's not. But we do get some really funky colours. I think one of my favourite one, we call it our unicorn fireball. It actually starts off like a light blue, and it turns to purple, and it turns pink, and then it goes red. So that the colours of the fireball, there's a few things in there. So like I said, about 97% of what you're seeing is the atmosphere burning. So it can tell us a lot about the composition of the atmosphere, but also there is that element of what's actually in the rock. So iron usually burns green, which is why a lot of these meteorites are iron rich, and that's why you usually get a greeny colour.
There.
Out of the 100 grams that enters the Earth's atmosphere every year, how much makes it to the ground?
How much makes it to the ground of all the ones that enter?
Was that 100 grams per day?
Oh, that would be at the top of the atmosphere, for sure, yeah. So the Desert Fireball Network across Australia observes 3.5 million square kilometres of sky. It's about a third of Australian skies, and over that we see about one fireball a night. So that's as bright as Venus or brighter, all the way up to the full moon and more. And we reckon every year we maybe get 5 that drop on the ground.
Yes, Doug.
I noticed you haven't got any in Victoria. Do you think there'll be some in Victoria that's maybe?
We do have collaborators at Monash University, and they have 2 cameras that they are due to put out.
Excellent. Tom.
Haha, very good question. The question was, did we manage to get any data for the Alice Springs fireball that happened earlier this year? That was it was too far north for our cameras. We did do a lot of work with it, though, actually. There's some casual video footage, especially from the local police station, and we have managed to get a rough trajectory, but the full line on the ground, or full area on the ground for us, is still way too large to search. But the interesting thing with that one is the way we've calculated the trajectory. A lot of it is actually from the sonic booms. So there's infrasound sensors, are basically really sensitive seismometers around the world that are listening for these sonic booms, and you can actually backtrack and figure out a trajectory through the atmosphere from just the sonic booms.
One last one.
What did you find out about the earliest stages of the formation of the universe from the Lily? Was there anything in particular that was found from examining that fragment?
They're still analysing, really. We know that it's not nowhere near as special as Murchison. It's what we call an ordinary chondrite. So they're still analysing the data from it, but it doesn't have anywhere near anything as special as Murchison. So it's pretty typical, but it is really nice. Actually, of the 5 that we've found, 4 of them have been ordinary chondrites. But it's nice to kind of get that confirmation of the percentage of ordinary stuff versus unique stuff, and it really shows us how special that unique stuff is.
Thanks, Ellie. Look, this is just fascinating, embracing some really cool new technology, and the thought that we can all have an app on our phones to help track some of these things is really, really great. So a little token of our esteem, thank you for coming over from Perth.
Thank you very much for having me.